Hello everyone. In this talk, I will introduce Flow Contrastive Estimation, or FCE, a unified generative framework that bridges two major classes of generative models, energy-based models and flow-based models, in a noise-contrastive learning framework. We'll discuss its motivation, theoretical foundation, and applications in density estimation, image generation, and unsupervised representation learning. Flow Contrastive Estimation, or FCE, is a joint training of two types of generative frameworks, energy-based models and flow-based models. The energy-based model captures complex dependencies among data points and provides a scoring function that measures how realistic a sample is. The flow-based model establishes an invertible mapping between latent and data spaces, which allows exact likelihood computation and efficient sample generation. In the following slides, we will discuss how these models can be incorporated into the noise contrastive estimation framework. In this slide, we will talk about the motivation of flow contrastive estimation. Let's recall the foundation, noise contrastive estimation. In noise contrastive estimation, an energy-based model is trained discriminatively by distinguishing real data from samples drawn from a Gaussian noise distribution. However, this Gaussian noise provides only a weak contrast. It's too far from real data to effectively shape the energy landscape. Flow contrastive estimation improves upon this by using a flow-based model to transform the noise into a distribution closer to the data, creating a stronger and more informative contrast for the energy-based model. At the same time, training a flow model with maximum likelihood estimation alone tends to produce overly smooth and blurry distributions. Flow contrastive estimation modifies the maximum likelihood objective to approximate Jensen-Shannon divergence minimization between the flow-based distribution and the data. This correction sharpens the learned distribution and improves sample realism. Let's introduce the energy-based model. Let x be the input variable, such as an image, and let p of x represent the model's probability density function. The model parameters are denoted by theta. The energy-based model defines this distribution as an exponential family, where f of x represents a negative energy function or scoring function, and z is the normalizing constant. The function f of x is parameterized by a bottom-up neural network, while z is analytically intractable, making the energy-based model an unnormalized probability density. The training objective of the energy-based model is to learn a scoring function f of x that assigns low energy to observed examples and high energy to unobserved ones. A standard approach to train an energy-based model is through maximum likelihood estimation. The gradient of likelihood is given by the following equation, where the expectation can be approximated by averaging over the observed examples, p data, and synthesized samples generated by the model p of x, respectively. However, sampling from the model p of x requires Markov chain Monte Carlo method, which can be computationally expensive and may take a long time to converge. Noise contrastive estimation is another method to train an energy-based model without using Markov chain Monte Carlo method. Firstly, instead of explicitly computing the normalizing constant z, NCE treats log z as an additional parameter c to be learned. Suppose we have observed real data samples and generated samples drawn from a noise distribution Q. The model parameters theta can then be estimated by maximizing the following objective function. This objective function aims at training the model p of x to distinguish real data and noise samples, effectively turning density estimation into a binary classification problem. The objective function of NCE connects to logistic regression. For each example x, we assign a binary label y. If x comes from the real training dataset, y is equal to 1. If x is generated from the noise distribution, y is equal to 0. We assume both classes are equally likely. Under this assumption, the probability that a sample X is from the data distribution given by the model is P over P plus Q. This is a component in the NCE objective. We denote this probability as U of X with parameters theta. Then, the log likelihood for this logistic regression classifier can be written as below, where the first term corresponds to real samples, and the second term corresponds to fake samples. Second term corresponds to noise samples. In other words, the model is trained to maximize the probability of correctly distinguishing real data from noise, which is exactly how NCE allows us to learn an unnormalized energy-based model without explicitly computing the partition function. Now let's talk about normalizing flows. The idea of a normalizing flow is to define a bijective transformation between a simple latent variable z and the observed data x. We start by sampling z from a known base distribution, usually a Gaussian distribution Q0. Then we apply an invertible transformation g with parameters alpha to obtain the data sample x. The key property of this transformation is that we can explicitly compute its Jacobian determinant, which allows us to evaluate the exact density of x. In practice, G is built as a composition of multiple simple invertible mappings. Therefore, the log likelihood can be computed by summing over the Jacobian determinants of each transformation step. This property makes normalizing flows both tractable and powerful, as they allow exact likelihood computation and efficient sampling. Continuing with normalizing flows, the key design principle of flow-based models is to construct transformations whose Jacobian matrix is triangular. Why is this important? Because for a triangular Jacobian, the determinant, which appears in the change of variables formula, can be computed efficiently as the product of its diagonal elements. This design allows us to compute exact log likelihoods without expensive matrix operations, one of the main advantages of flow-based models. Finally, the training objective for the flow model is straightforward. We use maximum likelihood estimation, which is equivalent to minimizing the KL divergence between the data distribution and the model distribution. In short, the model learns to make flow-based model Q as close as possible to the true data distribution. Let's now compare energy-based models and flow-based models. Starting with energy-based models, their main advantage is flexibility. The energy function can be implemented using any neural network architecture, such as a CNN. In addition, through Bayes' rule, an energy-based model has a direct correspondence to a discriminator, which makes it conceptually close to adversarial training. However, the main drawback is that maximum likelihood learning for energy-based models requires Markov chain Monte Carlo sampling, which is computationally expensive and often slow to converge. In contrast, flow-based models offer a different trade-off. Their strength lies in providing an exact likelihood formulation. We can compute the exact probability of a data point and also perform direct generation through ancestral sampling. On the downside, these models require carefully designed invertible transformations, which can be unnatural or restrictive in structure, and they tend to be less flexible and less effective for feature extraction compared to energy-based models. Recall that NCE reframes density estimation as a classification task between data samples and noise samples. The objective function encourages the model to assign higher scores to real data samples and lower scores to noise samples. One key design question in NCE is, how should we choose the noise distribution Q? Ideally, Q should satisfy three important properties. First, it should have an analytically tractable and normalized density so that it's easy to compute. Secondly, it should be easy to sample from, since we need many noise samples during training. Thirdly, it should be close to the data distribution, so the classification problem is neither too easy nor too hard. If the noise distribution is too different from the real data, the task becomes trivial and the model learns little. So, The success of NCE relies heavily on choosing a good contrast distribution Q, and this motivates flow contrastive estimation, where the noise distribution is learned adaptively through a flow-based model. Now let's look at how the energy-based model and the flow model are jointly trained in flow contrastive estimation. The idea is to iteratively train both the flow distribution Q and the energy-based model P so that the flow becomes a stronger and more adaptive contrast for the energy-based model. This training scheme is conceptually similar to a generative adversarial net, where the two models play a mini-max game. The energy-based model tries to assign low energy to real data and high energy to flow-generated samples. Meanwhile, the flow model learns to generate samples that are closer and closer to the data distribution, effectively trying to fool the energy-based model. Let's break down what each term means in the objective function of flow contrastive estimation. When we maximize with respect to the energy-based model P, we are effectively performing noise contrastive estimation. The energy-based model learns to assign higher probability to real data and lower probability to flow-generated samples. When we minimize with respect to the flow model Q, the flow is trained to minimize the Jensen-Shannon divergence between its own distribution and the data distribution. This decomposition gives us two complementary forces in training. The first term behaves like a weighted MLE, encouraging mode covering, making sure the model doesn't miss any data modes. The second term behaves like a weighted reverse KL, which emphasizes mode chasing, focusing the flow on generating high-quality, realistic samples. Together, these two objectives create balanced cooperative learning process. The energy-based model serves as a discriminator to train the flow-based model in adversarial training framework, while the flow model provides a strong, adaptive contrast that helps the energy-based model learn a sharper and more accurate energy landscape within the noise contrastive estimation framework. Flow contrastive estimation is a general framework that can be applied to a wide range of domains. First, in density estimation, it allows us to model complex data distributions while keeping the likelihood analytically tractable thanks to the flow-based component. Second, in image generation, FCE can produce realistic and diverse images. Finally, in unsupervised feature learning, FCE helps discover meaningful representations directly from unlabeled data, providing a solid foundation for downstream tasks like classification. We first present the application of flow contrastive estimation in density estimation. This figure illustrates the results of FCE on several two-dimensional distributions. The learned energy-based model accurately captures multimodal distributions and achieves a better fit to the data than flow-based models trained using either FCE or maximum likelihood estimation alone. Next, let's look at image generation. These examples show images synthesized by the flow-based model learned through flow contrastive estimation. From left to right, the panels correspond to samples generated from the SVHN, CIFIR10, and CELEB-A datasets. All images are of size 32 by 32. As we can see, FCE is able to generate realistic and diverse image patterns across different datasets and visual domains, digits, natural scenes, and human faces. Finally, let's look at how flow contrastive estimation can be applied to unsupervised feature learning. The key idea is to train the model without using any labels and then use the learned representation for downstream supervised tasks. The process works in 3 steps. First, we perform flow contrastive estimation on the entire training set in a completely unsupervised manner. Second, after the model converges, we extract feature maps from the learned energy-based model, typically from the top layer or across multiple layers. These features capture the structure of the data. Finally, we train a linear classifier on top of the extracted features, using only a small labeled subset of the training data. To conclude, Flow Contrastive Estimation is a unified generative learning framework that jointly trains an energy-based model and a flow-based model. It effectively combines the strengths of both paradigms. The energy-based model provides expressive modeling power and learns meaningful energy landscapes, while the flow-based model offers tractable likelihoods and efficient sampling. Conceptually, flow contrastive estimation can be viewed as an adaptive form of noise contrastive estimation, where the flow model evolves to become closer to the data distribution, serving as a stronger and more informative contrast for the energy-based model. We've also seen that flow contrastive estimation can be applied to three major domains: density estimation, image generation, and unsupervised feature learning. Thank you for your listening.